I want to. So you said it was okay to boast like hirings?
Anything you want.
All right, cool. So my name is Stefan. I'm a crazy guy from Norway, running a startup on search, which is cool. And we are looking for co-founders and technical geniuses to help make a cool search product. So if you are basically back-end developer or want to make a really nice-looking front-end for our product, come talk to me. And we are here for 3 months, so we can talk it over and try it out if you want to. So yeah.
Do you want to pick a spot where you want to stand, like after the meetup, in case people want to be like over here?
I'm gonna pick a spot. I'm gonna be over there.
And I'm going to
We work together. Yeah.
Excellent.
So Norway is cool.
Thank you. All right. Anybody else? This one back here? No? Okay, I'll make a quick announcement. So I work in search science here at eBay. We're always hiring excellent engineers and researchers, so I will be standing right over there if you want to come talk to me. If nobody else has any announcements, then I'd like to introduce Shawn from Dato or Dato. I guess it depends on whatever your preference is. He's going to talk about deep learning and image search, I think, which should be great. So thank you.
We always get asked, is it Dato or Dato? We're still letting the market decide. So thanks a ton for having me, Chris, Ron, Don, and Jake. Yeah. Super excited to talk about searching for images. So my name's Shawn. I'm originally a physics guy turned data scientist. I've taken basically everything but the shortest path to get here. So I started off in physics, got a PhD in materials science where I did device physics, trying to make solar cells more efficient. And that took me down the path of simulating devices a lot. And so I spent about half my time writing simulations of the devices, and then the other half doing measurements and a bunch of data analysis. And that led me ultimately into doing data science in earnest. These days, I love predictive apps. So that's me. Who's Dato? Who's heard of Dato or Dato? Just a few. What about GraphLab? A couple more. The sets are not exactly the same. So Dato's, this is us. We're a company, a startup, about 2 years old. We're in Seattle. We're a little over 30, I think we're up about 35 people right now. This isn't all of us. And we started off as an academic project about 7 years ago at CMU, doing something a little different than we do now, which is basically doing really, really large-scale graph analytics. And that's what the original founding team got known for, which is basically how to do things like PageRank or triangle counting, sort of prototypical graph analytics tasks on really humongous scale graphs. Turned out that we were really good at building systems like that. And people started asking for the code, and we open sourced a bunch of the code. And then we started getting interested in recommendation systems, and so we built a collaborative filtering toolkit for GraphG, which was one of the open source projects. And people started asking more and more for this stuff, and we had a couple workshops, which, unlike most academic workshops, were not the typical 30, 40 people that show up. Our first workshop was something like 200 people. The second year we were over 350. Last year we upgraded to a conference. So we at the time it was the GraphLab conference, and we were over 700 people last year. This year we have a 2-day, it's called the Data Science Summit and Dato conference, and we're shooting for a little over 1,000 people. So that basically all came because of the code. 2 years ago, we had a choice. We founded a company, which originally was called GraphLab, now called Dato. And we founded it for something slightly different. Rather than just commercializing this super fast graph analytics engine, we wanted to do something a little different, which is basically to make building predictive apps easier. So we're all super geeky about the intelligent things you can do with machine learning. And usually I have it on my wrist, but I don't today. Instead I have this lovely wristband. But these are all, if you think about all the killer apps that are out these days, every single one of them is killer because it has intelligence at the core. They're using machine learning to do something disruptive. One I always highlight is my watch here. This is the Basis B1 smartwatch. And when I bought this 2 years ago, it was the only smartwatch that would automatically classify whether I was walking, running, or cycling. I'm a cyclist, and I want to keep track of that stuff. And so that was the killer app for me. Now there's the iWatch, which is totally going to displace Basis, but they're the first. So we're excited about the applications, and we know all of these, recommenders, fraud detection, this kind of stuff. So what are we, the team at Dato, what are we about? We're about this concept of going from inspiration, you have an idea, to production. How do I make that idea not only practical, go through that proof of concept stage, but go all the way to a scalable service. Ultimately, that means basically making all stages of that process easy for developers and data scientists. So not only developing the idea, but deployment and then management of those predictive apps once they're deployed. We are super interested in enabling you to create not only the same things that you already create faster, but also enable you to create new applications that just weren't possible before because it was too much work, too much low-level stuff. So we have a platform which is built for folks like us. There's 3 components. GraphLab Create is basically the core tool that you use to do your prototyping and development. The fundamentals are built on these scalable data structures. The S-frame, which is a columnar data structure that's on disk. So columnar means you're fast for analytics operations and machine learning tasks. On disk means that you can scale the big data. We have an S-graph, which is a graph representation that's built on top of that. Tons of machine learning. Today we're going to talk about deep learning and nearest neighbors combined to do image search, but we have all sorts of stuff in machine learning. And then for deployment, we have 2 products. One's called Predictive Services, and this basically is built so that you don't have to stand up the boring web service code over and over again. So once you create a model, just in a couple lines of code, you can turn that into a scalable, elastically scalable, fault-tolerant service, and we do things like model versioning and all the management stuff that would usually be a pain to build. And then for, let's say you have some complex data pipeline, and there's a bottleneck, you have some task, it's taking a day, you need it to finish in half a day, we can do parallelization for these tasks. So that's my marketing pitch. We're also hiring, which I'll mention at the end. I have 3 demos, and we'll dive into the details basically of some of the fundamentals of deep learning and how it applies to this, and then do a simple example of image search. Okay, but we're going to start off with funny. Say what I mean. So who remembers when Google first came out with what was called reverse image search? Okay, so here's how it works. I'm going to copy an image. If we go to Google, and I want,
You're not mirrored.
I'm not mirrored. I see. That's clever.
There we go.
Sounds good. Okay, Google Images. So I paste in something, and then I get this little link up here that says, for matching images, try search by image. So that's what I'm reading. So this is search by image for me. This is my the team page. So what we see back, so this is now, I don't know, 2-3 years old. So given that image, we're given responses back that are pages that include matching images. And so it's not just simple match, but also if things are resized or different resolution, they'll find that. So that's one application. And then there's this interesting one down here, which is visually similar images. You can see what's visually similar. This is my favorite one, I have to say. Well, it's a toss-up between Mel and this guy. Okay, so obviously you're picking up on the core part of the image, which is that I'm a very handsome man. So beards, obviously. So that's a simple example of image search. So what are the applications and stuff like this? So if you think about basically all of the data products that we have built over the last 5-10 years, a whole lot of those products are built on squeezing the most we can out of text. It's about finding features that describe documents, bag of words, or concepts within those words, and then we build all sorts of stuff with it, right? We haven't done much with images. Images are pretty early compared to all the applications we have using text features. So just thinking about all the things that we use text for, a lot of those same things apply here. So things like recommendations or item search is the most basic. So sort of extending the concept of more like this, only where my this is an image, right? Deduplication, this turns out to be super important, very practical across all sorts of customers we talk to. So if I'm someone who has multiple data streams, or even someone like eBay where I have multiple products on the same site, how can I very simply identify that that's the same image? Zillow, one of our customers, the core issue they have is they get house listings from different streams, and they have images that will be slightly different resolution. And so they need a very smart way so that they don't show 100 images where only 20 of them are actually the unique set. Fraud and finding rule breakers. So if you've ever bought anything on Craigslist, every once in a while you'll notice someone posts something like, I don't know, some crazy new looking Mustang for a bike. And you also see that they post that same thing for something else that's not a bike. You'll see the same image show up a lot. Personals, it shows up a lot. So that's another application. And then rule breakers, Zillow has this rule, and I think others have something similar, which is basically if you post an image, you can't have text on the image. So being able to identify that is important. Medicine, all sorts of applications, but just imagine you're in charge of a bunch of NMR images, and you're trying to find other cases that are related to your patients. So I want more like this brain scan, right? Or how about just new cool apps, new ways to interact with other stuff? Build something to make me care more about art history. Okay, so how does image search work? To get there, we're going to just start with a brief step on machine learning, and then go into deep learning, and then to image search. So if you, who doesn't know, who doesn't use machine learning actually as sort of part of their day-to-day work? Everyone uses machine learning as part of their day-to-day work here? Okay, good. So then you guys can tell me what this is. So this is one of the earliest experiments and applications of machine learning, the famous Rosenblatt experiment. And what these guys did is they had this thing, which was something like it was either a 20 by 20 or 40 by 40. It's like 20 by 20, 20 by 20 photocell grid. And then the task was to detect shapes. So this is the earliest image recognition that was done. But all of this was super mechanical. So they had actual photocells, and then they had potentiometers that were on each of these leads in the back. And the task was, based on this mess of signals that are coming out, and given various electronic weights between the signals, how can you find the right weights so that you can learn the shape that you're seeing? So machine learning, of course, is where we have input data, We have some sort of parameters that we can tune so that we can optimize for some functions so that we can learn with more data. Okay, how about deep learning? So to go to deep learning, we'll start with machine learning. So a very, very simple view of machine learning is you have data that goes in this case maybe it's an image of a cat, and then you get some response or prediction out of this black box, where that black box is an algorithm. So let's say that's any algorithm, any machine learning algorithm. That was strange. Give me 1 second, something's out of order. Okay, all right. Oh, I see. Right. Sounds good. Right, so machine learning. And then the standard process we all follow is generally supervised. So meaning we have some sort of label that we're trying to predict. And so this starts with some sort of labeled data. I do things like create train test splits. I create a model, and then I validate the model and usually learn that it's not good enough and I need to do more work. And so that leads me to either adjusting those hyperparameters, so tuning the knobs, or going back to my data. So let's look at a very simple example of that, and then we'll dive into deep learning. Okay.
Shawn, can I ask you to speak just a little bit louder or use the mic?
Yeah, you bet. Okay, so in this case, we're going to do a very, very simple machine learning task, which is to build a neural net classifier to classify whether or not there's a car in the image. So very simple. So we're going to go through those same steps. And in this case, I'm going to use GraphLab create. So here I'm going to load some data. And I can take a look at what the data looks like here. So these are black and white images. And you see these are the first 4 that are in this set. And you see the top one and the bottom one are clearly not cars, and the 2 middle ones are clearly cars. And I can also see this is basically the weighting of the positive labels and negative labels, or number of cars, number of not cars. And I see it's reasonably balanced. So now I'll create a model. And we see here we're using an existing neural net model. See, there's a bunch of details here. We'll come back to this. So in this case, I'm feeding in that training data, and I'm trying to predict the target, which is the label, whether or not it has a car. Okay, so this is done, and then usually I do something like evaluate the model. So I look at something like this, a truth table, maybe the overall accuracy, or if I'm fancy, I might look at precision recall or some sort of information retrieval metrics. So in this case, we see we're really good at predicting whether or not there's cars in here. So that's cool. So that's a very simple example, and I was actually using deep learning. We'll go deeper. So what's special about deep learning? Deep learning, what's special is basically that black box, what's inside. It's the same task, only in this case we're predicting cars instead of cats. Who uses neural nets actually in their work? Who knows what neural nets are? Almost everyone. Okay, sounds good. So what's crucial here? Obviously deep learning is all the rage these days. So there's a meetup this week, there's a meetup next week on the same stuff. And there's a couple reasons that it's I would say, popular these days. A lot of it has to do with the applications that are now possible given GPUs. At the end of the day, deep learning is just another sort of rebranding of neural nets. And the sort of fundamental concepts here are that you have input, and then the model is basically a complex set of functions that connects those inputs to different layers. And you can think about going between each of those layers as a set of transformations. Where here, typically, this is something like a sigmoid function that depends on some number of these inputs that are adjacent. People always talk about the topology of a neural net, so that's basically the specific architecture of this. And there's a couple details that matter. So in general, neural net has multiple layers. The input is something like an image. The output is something like a prediction. Then we talk about convolutional nets, which are used a bunch these days. And basically all this is rather than having every input connected to every element in a layer, those middle layers, you are strategic about how you'd make those connections. And so this is showing rather than connecting everything, we just connect a few. And then those middle layers, there's two kinds of layers that matter. There's the so-called convolutional layer where you create convolved features in that transformation. And so in this case, there's a certain operation. If you look closely, this is basically saying, okay, take everything that's diagonally related to this and sum them up. So I see 1 times 1, 1 times 0, plus 1 times 1, 1 times 0 times 0, 1 times 1, and so on. Add those up, and I get a 4 here. And so I'm taking that, if this is, let's say, an image, those are pixel intensity values. And then I'm compressing those down to a single number. And I can go through my entire image and do this. And so now I've just transformed that input to a new representation. The other kind of transformation that matters is what's called pooling. So this is similar, but where we take, for a certain patch of the image, we do things like take the maximum intensity of all the pixels in that range. And that's important for identifying the centers of certain objects. Same kind of idea. We're doing a transformation on a set of pixels and then representing it as some reduced dimensionality feature. Okay, so that's the basic stuff. Who's seen this image before? A few of you guys. So this is, was anyone actually involved in the project? No, okay. So this is sort of a famous, these days, famous topology. And it's a very specific architecture used to train an image classifier, a multi-label image classifier, on a data set called ImageNet. So this is Jeff Hinton's research group. And basically each one of these layers, each one of these segments is a layer. And then those domains are different transformations. They describe how each of the layers are connected together. So you see it's pretty complicated. Something that's maybe not obvious, those transformations turn out to be fundamentally related to matrix operations. And so just like doing, just like solving eigenvalue problems, it turns out that GPUs are good for that. GPUs are also good for these kinds of tasks. So it turns out if you're doing very large scale image problems with deep learning, it's important to be able to run on GPUs. Okay, so when I look at this, and I look at running stuff on GPUs, doesn't sound like the easiest thing. You know, for me, I started off in physics. I learned machine learning to solve tasks. I didn't learn the details on how to construct a 27-layer neural net. But I'm still interested in the application of this stuff. So in general, we're really interested in figuring out how to create an easy button. And I'll show what we can do there. So we started off with that simple demo. Let's go to one that's slightly more complex. So this demo, which was up earlier, this is using our whole platform where we've trained a neural net, which is that same ImageNet, crazy topology from Jeff Hinton's group. And then we took that model, deployed it as a service that's running on Amazon. And so now it's a live RESTful service, and you can query it with any image. And so in this case, unlike the cars, I didn't look at the details there. That was a pretty small data set. Here we're looking at 1.5 million images and 10,000 different labels. So we can predict some interesting things here. So the way this works, given an image, I can make a prediction of the things that the image is most likely to be. So in this case, this is a balloon. This was in the training set, so it's a balloon. I can click on something else. Image is sent up, predictions come back. Tiger shark, this was in the training set, tiger shark. So that's cool, but of course what's always most interesting is when you feed in images that weren't in the training set. So, if Getty responds to me. So what this little widget does is it finds images from Getty for me. Okay, so let's say something like, I can click on this guy. So this is not in the training set. It seems very confident in whatever this is, and this is an oscilloscope. So that makes sense. So this is also a very basic application of image stuff, but you can imagine it's pretty powerful, right? But we can do more easy things that is relevant to you guys. So to get there, we started off with a really simple API so that you can basically create neural nets without having to know all of the details of the topology. So we have a bunch of pre-built topologies. So Jeff Hinton's topology that's been shown to work for that kind of stuff, you can just plug and play and run. But something else that's super fun and relevant is, it's a good, easy button. It's called feature extraction and transfer learning. How about there? Who knows what transfer learning is? Only a couple there. Transfer learning is a very, very simple concept and very powerful for this kind of stuff. So the idea is you train a model on one task, and then you use that model for some other task. And so, simple example, I learned to walk, and then I use that knowledge to learn to run. I use that knowledge to run. Or I train an image tagger to do something like recognize cars, and then I use that tagger to recognize trucks. The general concept here, you've probably all seen images like this top one. This is sort of representing what happens to an image as it goes through a neural net through all those transformations. The idea of transfer learning is rather than going all the way to the end where you make a prediction, you're going to stop somewhere midway through and then just extract whatever the representation is of that of the data at that point. So it's something like stopping here and pulling that out and then feeding that into some other task. Could be a classification task, could be a nearest neighbors task, could be a clustering task, so on. So here the process is just slightly different than we did before for standard machine learning. So typically I'm starting off with labeled data, and then I've created a model using that labeled data, and then I'm going to use that model as a transformer, basically. So I'm going to use that model to extract features from any new, in this case, new images, and then I'm going to build a simpler model and just use the representation of those images that I get from that feature extraction to do something else and make something cool. Okay. So let's see how to do that. I won't show this now, but this is a hilarious video. Okay. So in this case, we're going to do transfer learning, where we take that initial model that we train the ImageNet, train with the ImageNet data set, and then we're going to use it to find shoes. Okay. And so let's take a look at the data first. Okay. So I look up here, there's 6,000 images here. So it's not a huge data set. It's huge considering it's all shoes, only from Nordstrom. So Nordstrom has about 6,000 women's shoes. And these are what they look like, okay? So tons of different kinds of shoes. So what I'm going to do here, can you guys see this okay? Is I'm going to take that neural net model, the ImageNet model. I'm going to load it. So this is a pre-trained model, and we actually offer this here. You can grab it. And let's take a look at the model. So originally this had a little over 1.3 million, this was about 1.3 million examples used to train it. There's a little bit of data here. Okay, so let's take a look at that first image. So the way feature extraction works, we're going to take an image and then feed it through the neural net and just extract that last layer that represents the image. So this is the image. I'm going to use this, and then I'm going to extract using that model. Just dot extract features and feed in that image and see what we get back out. Okay, so I see I get back for that one image, I get one row, which is basically a sparse array. Okay. So this doesn't mean much, but one useful way to think about this is that image that went in was 256 by 256 pixels, and there's 3 color channels. So think about what the total number of dimensions was going in and what the resulting number of dimensions is coming out. So we had almost 200,000 dimensions representing that image, and then we reduce it down by pushing it through that neural net to a little over 4,000. And that's, for anyone that plays around with things like nearest neighbors, that's meaningful, because if you get too big in dimension space, then you can't build good models. So this is basically, one way of thinking about this is a dimension reduction process. Yeah.
Do all those zeros mean you could reduce it further?
Not necessarily. So so other images are going to have something else in place of that 0.
Oh, that's perpendicular.
Yeah.
Okay,
Yeah.
all right, sorry.
I don't know that we have the best reduction, but
Is that still using the, passing it through the AlexNet, or is it?
yeah, exactly. Okay, so that's just a simple example of how you should think about this. We've gone through and extracted features for all the images. It's about 200 images per second, which is pretty fast, but not quite fast enough for us to sit through here. Okay, so I've extracted features. My next step is to create a nearest neighbors model. So I'm just going to take those features and use nothing else, and then just say, okay, which vectors are close to this vector, and which vectors are far away. Very simple. So I'm going to feed in the images, and then the features are those extracted features. So in this case, this is pretty fast. It's only 6,000 images. We can use brute force nearest neighbors. If I had tons and tons of images, then I'd care about other forms of a nearest neighbor model to make that more efficient. So things like ball tree or using hashing to get approximate search. Okay, so now I have a nearest neighbors model trained on those features. Now we can query it, so we can actually do some searching. So let's take a look at one image here. Okay, so this is a high heel. It's clearly a pretty airy high heel. Let's look for similar images. So I'm just going to take that nearest neighbor model and then query it given this image as an input. Let me get these out. And so what's the important thing? So these are basically the indices of the different image. And so I see I get a ranked list, and it's ranked by distance. So in this case, we were just doing simple Euclidean distance between those vectors, those arrays, the feature arrays. Let's look at these. So this is the query, and then we see the 9 most similar images. Not bad. Okay, let's try something totally different. cowboy boot. It's closed. It's brown. So we're going to do the same thing. Only this time I'm going to query for all. So we can do some fun stuff. Okay. So here's my query, and then 9 most similar. I see there's one other cowboy boot, and then lots of other boots that are brown. Does this make sense? Okay. So those are the top 10 most similar. So that's fun. How about the least similar? So we have all 6,000. So all we have to do is just go down to the bottom. So it's a ranked list. We just go down to the bottom distances. So let's look at those. So it turns out that there's more than just shoes here. There's some accessories. So clearly a cowboy boot is different than whatever this is, or whatever these are. So that makes sense. How about something a little bit more convenient? Something that's still shoes, but far away. So I'll just pick something that's right in the middle of that distribution. So let's look at these guys. So this is about halfway through the list. The query was boot, and here I see no boots, things that are pretty anti-boot, things like sandals and lightweight shoes. So the last piece here, so all we're doing, the important concept here is just that relevance is basically equivalent to distance. And so if I just look at the top 10, bottom 10, and middle 10, we can just do a quick average and see what the average distance is for each of these. And so I see top 10, I'm in around 42 units. Bottom 10 is around 92, so close to 100. And middle is about middle, so around 71. So you can imagine building something, it's just all about understanding that distance and how that distance maps to your particular application for relevance. Any questions? Yeah.
How it could come out even if you put just a shoe in the middle? What if not? What was the other attribute which would only bring the shoes or sandals, something like only? What is that feature that can really make it like a shoe? It looks like amazing. You just by changing the distance, how exactly you can control whether it's a shoe or boot or whatever.
Oh, so it's more about. So it's distance for images relevant to your query. So we could have done the same kind of analysis for the high heel shoe. And we'd see something similar, which is probably in the middle of the high heel shoes ranking would be something like boots.
Is the transfer learning, which layer you pick, does it matter ending up with shoes or something new?
The short answer is it matters, but usually you don't, as a developer, you don't care. People have found out that, okay, well the bottom layer works best for this kind of task, and so then all you have to do is to choose that bottom layer. But for sure, as you go further and further up, dimensions are bigger generally, and you have different representations of the image. Yeah.
How immune are you to differences in scaling, lighting, all the things that make imagery art?
Yeah, totally. The answer there is it really depends. So you see this is, so the model that we were using was trained on, it's all about the images that you originally trained on. And so we trained on 1.5 million images that had objects in them. And it was about, so we could recognize whether or not there's a chihuahua, whether or not chihuahua is filling the whole image or is just in a part of the image. So that should suggest that it would work well for things that scale, but I actually I'm not sure without trying it out.
Haitians and
Rotations are fine, generally, because here you're not actually doing a, it's more, if you look at these, if you look at the images, it's more about things like how much white space do you have here, what's the contrast, what are the colors. It's about sort of the course structure of the image. And so this image, I am willing to bet if we rotated it, we would still get nearly the same distance. Yeah.
So if you used a typical dimensional reduction, like say, how does it compare?
So actually, I don't know what the short answer is there. Does anyone know the answer there? So the question is, I explained this as sort of a form of dimensionality reduction. And so can you do the same kind of thing but using something like PCA?
It doesn't look as nice, definitely.
Yeah.
Like if you go back and look at like the original like Hinton paper, where he talks about the sort of pre-training and stuff, they have some really nice images that they've done with like two-dimensional projections from PCA versus like RVMs or something. And it was the RVM, like, which is the equivalent of this, is it separates things beautifully, and the PCA is still just kind of a big clump.
You know, PCA is, it's trying to basically learn the correlations between different pixels, and that's a simpler transformation than doing here. So you can learn much deeper things. Yeah.
All the shoes in the dataset seems to have the same orientation to the photographer. Does it work if the shoe is taken?
That was the question.
Like the question was,
Yeah,
does it adapt to rotation and different scale?
Yeah. So my gut reaction is that it should hold up well to different orientations. But I think you're right, actually, that these are all the same.
But you
so
didn't
just directly how Nordstrom has them. So.
Okay.
The best answer is try it out.
Yeah, I think the images are normalized. They're in the same part of the same scaling and all, and that's where PCA works. But when you use neural networks, they take into consideration features.
That's for sure
Yeah.
true.
If you have some human face, then it will take a look at eyes and other edges, and it will find similarity between those features. It won't just look at the plain normalized image. I think that's the difference between PCA and the
Okay, good answer. Yeah.
Could you say a little bit more about, we talked about the processing involving feature extraction.
Yeah.
So what kind of features?
So that's so neural. You know, it's not that different to how we describe latent factors. You know, how do you describe what a latent factor is? You do some sort of matrix decomposition. What does that represent? We always try to map it to human things. We say, well, like if I'm building a recommender model and I learn a latent factor, I'm sort of learning the fingerprint that describes you, and learning something about your interests, whether or not you're someone that likes action movies versus romance movies. There's an analogous thing with the features we extract here, and we always describe them in human terms. We say things like, well, the features that are extracted are things that they map to contrast and texture and amount of white space. The reality is that's a total simplification of what's actually extracted. So I don't have a good, succinct answer there, other than it's a reduced dimension that sort of intuitively maps to some of those things, but it's not a one-to-one.
But, I mean, the processing, as you showed, it involves matrix transformations.
Yeah.
So a lot of this will depend upon how those matrices are designed.
That's right.
And many of them will be designed to enhance a certain aspect of the image or identify a certain aspect.
Correct.
So are there particular kinds of transformations that have been found to be effective, or do you just try randomly a lot of stuff and see what works well?
So the research world tries lots of random stuff with some intuition, but what comes out is simple things. So we went through a couple of these things. So I mean, you can even just look at these representations, and you can see there are things that are sort of like the things that represent like the low frequency features in the image, and there's often transformations that lead to that. If you looked at these simple examples, you know, a pooled feature. Pooled feature, you're saying, okay, I'm gonna go chug through these pixels, these blocks of pixels, and then I'm gonna collapse down that box of pixels to whatever the maximum intensity value is. And so that's
But I think
that's basically sort of smoothing out the texture. That's just one way of basically getting out the lower frequency components.
But I think the critical thing though is that a human's not going in and saying like this part of the network is doing the edge detection and playing
That's
with the
right.
matrix, and saying this part of the network is going to do texture detection and playing with the matrix. This whole thing is learned. All that's getting fed in is pixels.
We can talk more afterwards. But okay. So that is the simple example of using transfer learning. There's, of course, tons of other things you could do with those features. Once you have a vector that represents your image, then you can do things like clustering or classification. You can take those features, combine them with some textual features that you extract. Let's say that you're trying to classify a web page. So now you can do something like take all the images, process them through the feature extractor. Now you have numeric representation of those. You could extract text features and then do something like nearest neighbors on the whole document, or clustering on all your documents. Okay, that's basically the end of my talk. So a couple shameless plugs. I mentioned the conference that we have. It's coming up July 20th, 21st. It's in San Francisco. And I have, for anyone that wants to come, a super killer discount of 50% off. So just come grab one of these. So the first day, we're expecting about 1,000 folks. First day is general data science, machine learning. And the second day is all folks that are doing stuff with Dato, as well as training that we're doing. So that's coming up in the not so distant future. Go to conf.dato.com. Something that's more immediate, if you're eager to play with something like feature extraction or some of the other stuff we do. We're just starting off something with Galvanize. Does anyone know who Galvanize is? Okay. So Galvanize SF, we're doing Dato office hours up at their office starting tomorrow. So basic idea, bring your laptop and some data, and we'll sit with you and get started on whatever you want to get started on. It's tomorrow, 2:30 to 5, followed by some good beers up in Soma in San Francisco. So talk to me or email me, Scully@dato.com. And then other resources, get the software, download it for free. There's all sorts of stuff that you can build quickly. If you want to learn, we have a whole section with notebooks that describe all sorts of applications. If you want to learn more, we have a blog that goes into all the details. We're hiring tons, basically across the board. So machine learning engineers, general full stack developers, front-end web, and then folks to work with customers. Bug me. But more interesting than any of that stuff, I would love for you to just go create something super awesome, and hopefully using us. So that's what I got.
Thank you.
Happy for other questions?
I'm not
aspect of tensor learning, so it's kind of like a mystery to me, like how does it work? And like in particular in this case, did it really work well here because the ImageNet was just a model that was trained on so many pictures that maybe some of them were shoot. Versus say I take a model that only trained on faces or fish.
Yeah, totally. So the short answer is the set of images that you train on matters. But it turns out that the ImageNet data sets, it's general enough that you can extract these general features. So one simple example, we have a customer called Compology, who's up in San Francisco. They are trying to reinvent the waste management industry. The way they're doing that is they have webcams in a bunch of industrial dumpsters. And so their task, their goal is basically to efficiently use trash trucks. So don't go pick up dumpsters that are empty. So they have webcams. Every 2 hours, they send a picture of the inside of a dumpster. So they're images that are literally of garbage. And they're basically using exactly this process. So they're extracting features from their super low quality images of trash, and then they classify the fullness based on local data. So it's one data point, but there are many others out there that show it's pretty general. It's a good model to apply to lots of things.
Suppose I had a pile of GPUs. Can you guys make use of them?
Can we specifically?
Yep.
So today we run on GPUs. We run on right now. If you have multiple cores, we only use one. In the next release, the release after that, we parallelize across GPUs.
I guess a specific GraphLab question.
Yeah.
Not having used it yet. I'm giving a big aerial photo, and I want to identify that they're landscape of cars, and I want to identify all cars in there, like sections that represent something else.
Right.
Would there be something that helps me in that direction?
So you can, well, you need to, we don't have, we have sort of the high-level building blocks for doing some of that analysis. We don't have the utilities yet to, so what you would end up doing there is chunking up the image into different regions as part of your pipeline. So there's tools that exist that are useful for that. You'd use that for sort of that first part of the pipeline, and then feature extraction or image classification further in that pipeline as well. Yeah.
So in transfer learning, you took the shoes and you built a deep network that was classifying shoes. Then you stripped off all the layers except the bottom layer, and it did the same thing.
So I actually did something a little different, which was we took a model that was trained on the ImageNet data set. ImageNet has elephants, and sea turtles, and oscilloscopes, and balloons, and all sorts of stuff. So 10,000 different things. So we trained the model on that data set, and then used that model to process the shoes. And the feature extraction step was processing through that trained network, and then pulling out the features in the last layer.
But so it could also process your neural network could process, and it could process train, plane.
Yes. Yep.
And then you could do linear network like just train, or you could do it like you could use the bottom layer.
That's right.
Yeah.
That's right. So that's the general concept. That's the power. So you can now use this one model that was trained on one set of images, but then use it to process other kinds of images to do a more specific task. And it turns out to work pretty well. Yeah.
So when you take your big neural network trained on the ImageNet and you cut it to get like this vector feature that you used on the demo, do you cut it like at the very far end, or is it better to cut it in the middle so that it's a bit more general?
In this case, we're going all the way to the end. Okay. You can play around. You can choose any way you want to extract those features. As far as I understand, different tasks do you do better in different hierarchies or different level of hierarchy. But with this one, it turns out to be pretty good. I'll do this one.
Have you tried running measurement statistics to see how well you do? Like you just trained on shoes standing alone. Now look for people with shoes on. Where is the shoe in the image? And how often do you find it and how often do you miss it?
Yeah. So we haven't done that. What I can say is, so there's the famous dogs versus cats that Google came out with a couple of years ago. So it was well shown that you do better doing a two-step process where you feature extract and then feed into a different model than to use the neural net to directly classify. We have a blog post on that too. So you see that you do better to basically use feature extraction using a neural net, and then to feed those features into something like boosted trees to make the classification, then to just directly classify using the neural net. And the accuracy is actually pretty significantly different. So with that two-step process, it's something like 98% accurate, which is extremely high and state of the art. And if you're just using the neural net, you're down around 79%. So it's significant. But it always depends on the particular task. Maybe there's something particularly special about dogs versus cats, but so far it looks good. Yeah.
So the distance you were getting over that entire set was, it seemed to jump to 40, and then the far end was 90, Is the close stuff, is that just, would be translations of the original image, or what does that kind of sense of distance hold up over the entire data set? It seems odd that there's this big jump and it's only twice the distance to the far end of the data set, right?
Yeah, so what's that tell you? I think all that tells you is that the distances aren't calibrated.
Okay.
So they're on some arbitrary scale, and all you know is that it's monotonically increasing. It monotonically maps to some sort of scaled or calibrated distance. In reality, it tells you that I don't have anything more intelligent to say than that. Yeah.
So you've been focusing on image search with
Yeah,
deep learning. Dato, I know, does all kinds of other classification problems. I think and here, you've got ImageNet and Hinton and all of these, giant brains feeding research into the problem. Have you tried deep learning on some of the other kinds of problems that you experience in the industry?
Yes. So there's nothing. Deep learning happens to be good for images because there's not a lot of other tools that are good for some of these kinds of tasks. Whereas something like text, we have all sorts of tools that do well for these kinds of problems. But it also turns out that deep learning's been used for all sorts of tasks. So there's nothing special particularly about images. So you can, there's a good work on things like speech recognition and concept extraction.
Well, I'm just wondering, for you guys in particular, is there some area where deep learning has been advantageous versus other sort of, more traditional?
Images are the simplest example, so that's why we show it. You have to go, your problems end up being pretty complex if you have to do the sort of standard machine learning analysis approaches to do a task like this. But we actually, we have some examples of doing deep learning with context.
Just following up on the question before you.
Yeah.
Did you try like the first time distance? Because it seems like if all the closest bit images are within like 40 or 41,
yeah.
But it seems also that this means the angle is pretty small, so it's like a very small cluster. For example, if you have like two opposite ones, big angle, still distance is 40, but
Totally. I have not, but we have a bunch of different metrics. We have cosine, we have, I forget what it's called, but the non-normalized cosine, a number of other metrics. And you can extend your own metrics too. We'll try it.
I've heard of a project at Stanford where they have 126 or so different classifiers that they use for images, and then they try to differentiate what they're looking at. How do you compare to that, or?
We do not try to compare to that. That's the short answer. But you could build a pipeline like that using this. You should think about this task as one task, which you could do many such tasks and string them together as some sort of pipeline. You could do that.
Going back to the text, do you guys support recurrent neural networks?
I'm not sure, actually.
What is your roadmap like? Why I should go for it?
Why should you work for us?
Yeah. No,
No, why should you be a consumer?
Oh.
Because here, recently, a year ago, GraphLab was, I mean, studied.
Yeah.
Recently, we have been shifted to Spark.
Yeah. Right.
I just want to put in perspective, I did invest a lot of effort in GraphLab and all. After some time, people said, oh no, now it is Spark.
Spark, yeah.
Spark. I like the Spark, GraphLab a couple of years ago. I just want to again relook at it. But then I'm just seeing what is the roadmap like.
Yeah. So I'll say two things here. So Spark is awesome. And super, today Spark really shines on making Hadoop tasks faster, right? And so it's a very natural thing to go in, replace a bunch of slow pipelines with something that's faster now. In general, it's still kind of early days for MLlib. So in another 3 years, 4 years, they'll probably have a lot there, but today it's a relatively small, early library, let's say. But Spark is still great, and we integrate with Spark, so you can directly have a pipeline, create RDDs, and then without instantiating those RDDs, transfer them over to S-frames and do stuff in GraphLab Create. For us, the roadmap is about basically filling out the toolkits that we have today. So we'll be also adding more and more algorithms and also more task-oriented toolkits. So we have stuff for images. We have a recommender toolkit, which has something like eight of the most important algorithms for recommending. Things like factorization machines with an implicit loss function or ranking loss function. So that allows you to basically throw in not just co-occurrence, but data describing your items and users as well. So tasks like that we see are growing in popularity, so where it's sort of more application oriented rather than basically here's how you can tune all of the knobs of a neural net, which we still also expose, but the number of people in the world that are going to spend their time down there is much, much smaller than the folks that just want to build something cool and need something that works out of the box. So we'll be focusing a lot on that, and then more on our production pieces too. So today I can take one of these models, turn it into a fault-tolerant scalable service. There's more work to be done, and make that easier to be on-premise as well. And in the next release will be, so GraphLab originally was known as a giant distributed system that was super fast. And if you look at what we've done to date, it's been focused on how to get the most out of a single machine. In the next release, our Dato distributed will have distributed machine learning, among other things. So those two pieces, making sure that we can deploy easily, manage once deployed, easily. And then, you know, you think about any sort of practical task, you think about closing the feedback loop. And it turns out that folks don't have good options for a lot of testing and how that feeds back. So we'll be doing more there too. Happy to talk.
Thank you.
I should say, I traveled light today, so I have some stickers for swag, and feel free to come up and grab other stickers or a card to sign up for the conference, 50% off. If you want to come up to San Francisco tomorrow, I'll be up there. Come grab me, and I'm happy to talk.
Do you have one more, Frank?
Yeah,
This is a good question.
That's okay.
How do you differ from other companies like Hexdata's H2O or MetaMiners and other companies?
Yeah, so it's, I don't know, it's early days right now for companies that are commercializing machine learning platforms. There's pros and cons to all of us, and I think the market's huge and there's plenty of space for each of us. Hexadata's really, you'll ask Arna next week. So they're super great at scalable logistic regression, where input features are numeric, and they have some great things to get you started fast, which we like. If you care about text, if you care about doing images fast, today anyway, we're probably a better option for you. MetaMind is the other, and I forget, MetaMind is more of a machine learning as a service. So Hexadata and us, I would say, are similar in that we, like our target audience is you guys. People that are thinking about the problem and thinking about how do I apply machine learning to this, as opposed to sort of a plug and play, give me an API that just gives me the answer. Image in, classification out. And MetaMind and a lot of other companies are more focused on that, which you know, it moves you up the stack, which has its pros and cons. If you think that your data is particularly special, and you think that you can squeeze more out of your data than a generic model that's that everyone's using, then it's going to be better to choose a platform that you can not only get started fast, but then tune so that you can sort of be the most competitive that you can. So we see that folks that used sort of black box recommendation software like Rich Relevance, a lot of folks are coming away from that because if you're at Sears and using Rich Relevance, you basically have the same recommendations that you have if you're at Macy's and using Rich Relevance. So where's my competitive edge? So we're pretty confident that you can do more interesting things if you have some access to that notebook stuff.
Okay, cool. Let's thank Shawn again. If you guys don't mind, if you just pick up